It's very exciting to be here today, and I would like to thank Gordon and organizers to give us the possibility to show how we use machine learning applied to our user facilities at the Mag Lab. So maybe since we're in Tallahassee, I'd like to start by asking who has heard of the Mag Lab before? Okay, who has visited the Mag Lab? All right, okay, I'm very excited to bring everybody else on board as well. So introducing the Mag Lab is how we lovingly call the National Mag Lab that's here on the Southwest campus in Tallahassee. Our mission is to provide the highest quality magnetic fields as well as the scientific apparatus that go with that to the scientific user community. We serve a very wide range of disciplines. It includes physics, chemistry, material science, engineering, biology, geology, you name it. And you can already imagine with that broad background, we have a lot of varied needs for machine learning as well. So what we do is we develop our user facilities and services. We advance the magnet technology. We promote a multidisciplinary research environment, and we conduct a quite varied educational outreach program. So to be fair, the National Mag Lab actually is comprised of 7 user facilities across 3 sites. We have the site here at FSU. We have one at UF and one at LANL, Los Alamos National Lab in New Mexico. And today I'll be focusing on the FSU site. Essential to all those sites, though, are world-class magnets. And we have a number of world record magnets. And I'd be happy to talk about them in a lot of detail after this talk. We need our staff and their capabilities, as well as high performance and very reliable equipment. And we use or want to use in the future ML in furthering the impact of our facility by working on these 3 areas. Just to give you a little bit of a feel, we serve over 2,000 users a year, over 2,000 individuals conducting experiments in our spaces from almost 300 different institutions. And, there's also remote participation. So practically, what do we look like on the Southwest campus? We have our facilities, so that's the nuclear magnetic resonance, the ion cyclotron resonance. So the chemist part of the building, we have general lab spaces, and we have our DC very steady high magnetic field building, which has and features a lot of industrial style equipment. And you'll see in a minute why I'll point out this industrial equipment. So we're a 24/7 site. We have a huge magnet cooling water plant with very powerful equipment. Our power infrastructure, we are a 60 megawatt facility, which means that on a good day, we use 8% of the city of Tallahassee's electricity for our magnets. And we have a cryogenics plant. All of that to say that we have a large facility with lots of equipment, lots of sensors, actuators, and whatnot, all controlled by a distributed control system. So we're generating a lot of data, and even though we're a 24/7 facility and we have operators looking at the screens, there's a lot more going on than the human can capture and can look at. So what about machine learning in this space? So how can we leverage the capabilities towards organizational growth in our volatile, uncertain, complex, and ambiguous environment? Our goal is to provide the highest level of facility performance and impact, so high-performing equipment and very impactful research, while also protecting our personnel and equipment from what could potentially be a disastrous release of stored energy. Because we have all this industrial equipment, and there is the possibility of things to go wrong, and machine learning can come in very handy in helping us prevent those situations. And I'll talk about that in a little bit more. So I had already mentioned we need our world-class magnets, we need good staff, and we need the high performance and equipment. And I reiterate that because those are the 3 areas where machine learning comes in. Specifically, we would like practical approaches to enable facility performance and operational uptime. Concerning the equipment, we have a large variety of equipment. We have a lot of equipment for the space and for the personnel we have, and we have equipment in any part of the life cycle. So if machine learning can help us to keep the equipment capabilities maximized, that is a big plus. And I'll show you an example of how we do that. And then there's optimizing the human performance. And I put a smiley face because that one is always an interesting one. It's always the most difficult part to keep under control, quote unquote. So we do a lot of research into high reliability organizations and training, psychological safety and training, as well as personnel training. And we use machine learning in that process as well. And then there's expanding the impact of our research. This ties very much into fair data mining. I'll speak about that, as well as data analytics and aspects that machine learning can bring to that. So in short, we're basically looking for a smart and proactive asset management strategy where our assets are our equipment, our people, as well as the data that comes out of our facility. To start with the equipment capabilities. So we do research into high reliability organizations, and basically all of that factors around saying, hey, what if I could know about having a problem in the future? So what if I could spot problems before they actually happen? So as I said, we have equipment in every sector of the life cycles. We have these thousands of controls, but we do not have the people or the time to sit there and look through all of our monitoring data. So what traditionally would happen is that we would store that data away. And if something happens, we would go back and say, hey, what happened? Can we learn for the future? However, we know that they're gradual, very hard to spot for the human eye, but measurable equipment deteriorations, which can be a precursor to equipment failure. And what we're evaluating is at this point is the use of data mining and machine learning tools to basically develop programs that crawl through that data as it's being generated and that flags critical findings. Okay, so specifically for the proactive equipment maintenance, I would like to point out an effort that Abigail Centers is spearheading. She's also here today and she has a poster, so I encourage you to drop by Abby's poster later and have a look. So what we do here is we aim to proactively monitor our equipment. So what Abby is doing, she is looking at specifically for magnets. So specifically, we have a through cut of one of our magnets. There's lots of parameters that we monitor every day as we run these systems. And the work that she is doing is she is having algorithms look at parameters that are expected to behave in a certain way, and she's looking for deviations. But she's also predicting aging of specific components that we would expect to age. So in this way, we can do maintenance, we can plan for failures ahead of time, instead of having to do so when we have a user on site. Imagine you fly in from DC, you fly in from Europe for a single week of magnet time. You're here to do your experiment, and then MagLab has to say, oh, well, sorry, a component failed. We can't actually service you. That's a big problem. So if we can anticipate this ahead of time, this is a really big deal, and we can increase our uptime. All right, optimizing the human performance. Looking into high reliability organizations, those are organizations that safely operate close to 100% uptime. Think about aircraft carriers, nuclear power plants, and whatnot. We have looked at the principles that govern those organizations to learn and see if we can operate in a similar way, thereby improving the performance of our facility. So we're looking into being preoccupied with failure, being reluctant to simplify, be sensitive to operations, just to name a few, all with the goal to provide a safe and high user quality experience. And we started to utilize machine learning to help us with that. Specifically, we're working together with Texas Tech, the Center for Excellent and High Reliability Organizations, to develop machine learning algorithms that, quote unquote, take the temperature of an organization. So they measure the organizational culture, specifically with Texas Tech. And I would like to turn out Bernard Resnick, who has spearheaded this effort together with his supervisor, Tim Mattis. Specifically, what we do is we use our incident reporting system that we have at the MagLab, and we do machine learning text analysis of these incidents, the safety near misses, and we sort those, or the algorithm sorts them into topical clusters by an unsupervised method. And that can further, in a second project, we also analyze our organization for HRO readiness to see where do we fall in the landscape of being a high reliability organization. Importantly, this classification reflects the state of our organization, and it can inform high-level decision-making. Just to give you an example of that, So the unsupervised method where we sort the incident reports into clusters, it can help us find patterns and it can inform decisions. So if you look at this, you, for example, see in the top left corner, we hear a lot about ladders, contractors, stools, standing and stepping. So you can see there were a lot of reports saying, hey, we have people standing in a swivel chair. We have a contractor that fell. So similarly, if you look in the top right corner, there's more chemistry focused cluster. We can say, hey, cylinders, gas bottles, hood, chemical storage, there would be issues being reported with that. So importantly, by finding these patterns, we can inform our decisions as to where to put our training efforts and where to put our funds for our safety program. Similarly, working towards being a high reliability organization, we are looking at our HRO readiness. So we classify our incident reports into the HRO hallmarks. And here we distinguish between individual and institutional near misses and incidents. So based on natural language natural language processing, we can classify them and we can say, hey, this was an issue of sensitivity to operations. This was an issue with preoccupation to failure, or people here simplify. So this gives us a good feel for where in the organization the problems are. Is it an institutional problem? So are we not providing the right capabilities to our users and to our personnel to work safely? Or is it human decision making and we have to train the humans to behave in a different way? Also along the humans behaving in a different way, some further research that we're looking into, and that is something that is very interesting that I'd like to mention here, is that you can imagine that right now we're training this with safety incidents. An interesting aspect that we're looking into is to broaden this, to take a broader temperature or feel of your organization by adding any type of observation or adding this or merging this with our diversity portal. Because clearly organizational culture and safety culture are not fully exclusive, but this could really tell you a lot about, what is going on in your organization. And for example, how factors like employee voice factor into your safety program. Okay, further, we have FAIR data and machine learning. Excuse me. All right, so obviously, a lot of data comes out of our facility, and there's a big push nationwide, globally, as well as with the NSF, to make data findable, accessible, interoperable, and reusable, both for humans and machines. This is very challenging. The reason being that at this point, the data that we collect in our 7 user facilities is pretty fragmented and inconsistent in its data management practices. So you can imagine that a chemist that does ion cyclotron resonance or NMR versus a person that does condensed matter science has been trained differently in doing their research and also been trained differently in documenting their research. And so there's a lot of different approaches on how to archive your data. So at this point, there's also a lack of appropriate standards for this representation. And difficulties that we face are trying to teach researchers in different fields to implement changes in how they should be implementing or how they should be documenting their data. So what we do practically is that we work with the user facilities to standardize and automate the data as well as metadata acquisition. We work with the global research community, because again, we're an international facility, to establish those standards. And, we try to advocate and reach out and educate to staff and users to illustrate the value of data fairness. And that's where it becomes interesting for machine learning. Because there's a lot of effort in establishing FAIR at the Mag Lab, but there are also a lot of opportunities that come from it and that will make this effort worthwhile. For example, we're very excited about the Open Knowledge Network pushed by the National Science Foundation, which basically is illustrated in the figure on the top right-hand side, is to interconnect existing data and knowledge to enable AI, machine learning, to leverage data and information that's available to, address further challenges and give innovation opportunity. Along those lines, and as mentioned in multiple talks earlier today, we are very interested to see what role language learning models will play in future scientific research, specifically in, as you know, plausible sounding text that's factually incorrect can easily be generated. And, there are the questions of copyright and plagiarism there. And one thing that we're up against, while there are lots of opportunities for AI in looking at this fair data and reutilizing the data, is that, prominent journal publishers and journals have explicitly banned the use, since there are questions about the originality of the research. That being said, the MagLab is trying to navigate this landscape is excited for the opportunities there that could be there, rather than just looking at the data that comes out of a single paper and a single research project, having the fair data and having the wealth of information from our user facilities pulled together to see how we can leverage that to generate further knowledge. Also, questions such as can we outsource, quote unquote, certain aspects of data analysis to machine learning? Can we check our own literature research versus machine learning literature research, for example? All of this to say, what are we looking for as the MagLab in machine learning and AI? Well, I told you we want to predict issues to enable proactive remediation. Excuse me. We would like to be safer. We would like to have high reliability. We want to have safe time. We want to do more with less. We would like to recognize trends that are hardly human readable. And we want to gauge the state of our organization. We want to learn about our organizational culture, safety culture, and performance indicators. So machine learning and AI have an important role to play in the future of the research of our. All right, and with that, I would like to thank you for your attention and for the invitation. And we've seen a lot of things today, a lot of research. It would be nice if you think, hey, we have a solution for one of your problems. Abby and I are here, and we'd be happy to talk and see if you have ideas on how to strengthen the impact of our facility. Thank you very much.
Excellent presentation. Thank you. And of course, I just want to second what she said at the end. I mean, the whole spirit behind these expos is to really bring people together from cross interdisciplinary, cross modalities, bring them together and try and do something better as a whole that we could not have done individually. So please reach out if you have any interest. Let's open it up to a couple of questions if you guys would like.
So one of the issues AI models, it may not generalize new situation. I wonder, can you comment on how the model you have generalized maybe future cases or new cases?
Could you specify which research area you're referring to?
For the AI model, which model do you use? Do you classify? Do you use classifiers? Maybe everything.
Yeah, we have at this point we use, depending on the research project, it's different. It's not one effort. We have several different ones. If you have a specific, we can talk about that. Absolutely.
Okay, not so much a question, but a comment.
Mm-hmm.
A lot of people think that ChatGPT is not creative because it's based on the average of.
Right.
That's true if you simply ask a question with no additional.
Right.
But the fact of the matter is, it's really doing next sense prediction in some sense based on what you give it. So if you basically tell it to be creative, you point it to creative areas, say emulate the work of Richard Feynman or whatever,
yes.
Much more likely to get it. So I think a lot of people understand.
Yeah, I assume you're referring back to the fair data part where there are journals that ban the use of this technology because they say it's not original. Yeah. So actually in preparation for this talk, I thought, wouldn't it be nice if I could generate a couple of slides, with machine learning techniques and include them in the talk. So I was experimenting with this, and while I was very impressed with what came out of it, I was also very happy to see that there's still something that I have to add for FSU, as it should be. So yeah, definitely there. I was honestly shocked by how to the point it was, and as you were saying, you can guide the algorithm by saying, "Hey, think like X, Y, Z." So yeah, very, very much so.
Could you provide a little bit more details on how what success you're having with, or not, on predicting problems in the facility? Yes,
that is working very well. So we're currently we have a number of applications. Let me pull out two. So one of them is we're monitoring a certain voltage that is meant to be zero. So the generation of a signal there would be a problem. And we have been very successful or let me put it like this, in the past, we would have a failure happen because it's one of 10,000s of signal. And even though we have people sitting in our control room looking at screens all day, every day, they cannot be watching all those signals. Now we have protection systems to help us out if this, should something happen, hey, cut this off. So we're safe in that sense. However, then you're firefighting, right? A problem happens, you have a user there, the user gets delayed, you have to fix it while people are waiting. Are you ready? Can we go yet? So using the techniques that we have developed in-house and that Abby has spearheaded, we're now able to anticipate these kind of failures 4 to 6 weeks ahead of time. So that gives us the possibility to say, okay, we see a small voltage being generated. So there's a small change here. It is so small that, you wouldn't see it if you look at the screen, but, looking at the monitoring day after day as the data comes in, the algorithm can tell us, okay, something will happen here. And we're so far away from it being a problem that we have several weeks to react. So we can plan for that maintenance. And then, there is other predictions where we know, okay, this is a component that will age. So we're basically projecting a time series of how, an expected change that needs to be monitored. And it's very interesting to see that algorithm will tell you, okay, so many days out, I think things will happen. And we have very good experience with that.
In analog medicine, you make that most.
Yes. Yeah, looking at the small signals. Yeah. Exactly.
It's really encouraging to see all of the applications being applied to such an important research institution like the National High Magnetic Field Laboratory. And any of us here whom have expertise that would like to collaborate and continue to contribute to those laudable endeavors, please reach out to her. So please join me in thanking Dr. Julia Smith for her presentation.